Hi everyone, this is Kilabash. Starting today, we'll be releasing a series of tutorial videos, irregularly but continuously, focused on Photon 2, introducing new features and walking through the creation of simple VFX effects. Photon 2 is a powerful mod designed to help developers create stunning visual effects. Inspired by Unity, its core philosophy is to faithfully replicate Unity's particle system within Minecraft. You may have already seen how powerful Photon is and are excited to use it to craft complex effects. But before diving in, here are a few things you should know. First, Photon is not designed for absolute beginners in VFX. While it's not hard to learn, it still requires time and exploration. The best way to get started is by following Unity-related tutorials, as Photon and Unity's VFX system are conceptually almost identical. If you already have experience creating effects in Unity, using Photon will feel very familiar and straightforward. Second, Photon does not manage when, where, or how VFX are used. For example, attaching effects to entities or blocks, or managing their life cycles. While Photon provides some built-in commands, these are primarily for testing purposes. At its core, Photon is a VFX library and authoring tool, not a full usage framework. In the future, I may develop a separate mod to assist with VFX usage, but I want to be clear about the current design philosophy. Lastly, for those familiar with Unity, you might be wondering, how much can Photon really do? I can confidently say that Photon reproduces over 90% of the particle system and trail renderer features, and even partially supports line renderer. It offers GPU instancing, custom shaders, and GPU particle data customization, enabling some functionality similar to Unity's VFX graph. In general, as long as the effect doesn't require compute shaders, it can be implemented in Photon. If you have feature requests related to VFX, feel free to share them on GitHub or Discord. In this episode, we'll walk you through how to use Photon's visual editor and build 3 different effects. These effects range in difficulty. The first 2 are great for beginners to grasp the basics of Photon. The final one is aimed at more advanced users and will demonstrate how to use custom shaders and materials. Let's dive into today's tutorial. First, enter a single-player world and make sure you have creative mode enabled. Then, run the command /Photon Editor to open the Photon Editor. Note that the editor UI size varies depending on your Minecraft GUI scale settings. If the interface looks too large or too small, you can adjust it from the View menu at the top. Choose a size that fits your screen resolution for a better experience. The default layout of the Photon Editor consists of 4 main sections. On the left, the Hierarchy panel shows and manages the structure of FX objects. At the bottom, the Assets panel lets you create and manage materials, meshes, curves, and other resources. In the center, you'll find the main viewport, which is the camera scene for previewing and editing effects. On the right, the Inspector and History panels are used to set parameters and undo actions. All of these panels are fully customizable. Thanks to the new UI framework provided by LDLib2, Photon 2 supports flexible layout control. You can resize panel borders, drag windows between regions, and even split areas, just like in Unity. This makes the editing experience both familiar and powerful. Next, let's create a new FX project. Click File in the top left corner, then select FX Project. You'll notice a root node appears in the Hierarchy panel. Right-click inside the hierarchy to create a particle emitter. You should now see a default emitter appear in the scene view. The Scene Information panel shows basic info about the current FX. Click the Restart button to reset the effect, or click Pause to stop the playback. You can drag the playback time field to scrub through the timeline manually. The Seed field lets you set a random seed for the FX, so you can observe different variations. CPU time indicates the time spent per tick on logic updates, while frame time shows how long it takes to render each frame. In the scene view, you can drag with the left mouse button to rotate the camera. Hold the right mouse button and use WASD to move in first-person style. While holding the right button, press E or Q to move the camera up or down. These controls are almost identical to how Unity handles scene navigation. Let's expand the root node in the hierarchy and select the emitter we just created. You'll see a visual highlight showing the emitter's shape in the scene. If you don't want to see it, you can click Toggle in the top right corner to hide it. Now, let's create a firework effect. First, we change the shape of the emitter. Since fireworks explode in all directions, we'll choose the sphere shape. Use the radius parameter to control how wide the particles spawn. Because fireworks usually explode from a central point, we'll set the radius to a small value. You can adjust the number using the mouse wheel or by dragging the value field. At this point, you'll notice the particles are spawning one by one, which doesn't feel like a real firework. To fix this, set the emission rate to 0, then add a burst, set to trigger at time 0 and emit 150 particles at once. Click Restart and watch the effect. It looks great. Next, increase the start speed so the particles shoot out faster. Let's add gravity by enabling physics. Now the particles bounce off the ground like real objects. We'll tweak the gravity value and set particles to be removed when they collide. Now let's add a trail to make the particles leave a glowing trail as they move. This often makes effects look much cooler. Tweak the trail settings a bit to make it look smooth and appealing. We can also add color transitions using color over lifetime, then switch to the gradient. This allows the particles to fade or change color over time, like from yellow to red. If the trail is too long, reduce the lifetime so it becomes shorter. Then we use size over lifetime to change the particle size over time. You can use a curve mode to make them grow, shrink, or pulse, whatever suits your effect. Finally, don't forget to turn off looping so the emitter stops after the duration ends and all particles have disappeared. That's it, we've built a complete firework effect and explored many of the common settings in Photon. Now let's save the project. Click File, Save Project. Save it under the Assets folder as Demo 1 and confirm. Please note that the project itself can't be used directly in-game. You need to export it as an FX file before it can be triggered using commands or code. Now let's test the FX we just created in the world. Photon provides 2 commands that allow you to spawn FX and bind them to blocks or entities. You can find the full list of parameters in the Photon wiki. First, let's bind the FX to a point 10 blocks above the player's head. You'll see the firework explode in midair, just like it did in the editor. Next, we'll bind the FX to a pig. Since we used local space, the firework effect moves with the pig and stays relative to its body. Photon also includes other useful commands, for example, to remove FX bindings, clear cached resources, or delete all active particles in the world. Feel free to explore these commands on your own. Just keep in mind, Photon doesn't manage FX logic directly. If you need more advanced behaviors, please refer to the wiki for VFX APIs of Java. Now, we're going to demonstrate how to use sub-emitters to create a firework effect where particles launch into the air and then explode. Start by creating a new project. We'll use the default shape and slightly adjust the angle range to spread the particles a bit. Then reduce the emission rate to make the emitter fire fewer particles. Switch to real-world mode to view the effect in the actual scene. Check Enable Sub-emitters and add a new emitter. For the FX, choose the Demo 1 file we saved earlier. Set the sub-emitter to trigger on particle death and set the probability to 1 so every particle triggers an explosion. Restart the FX. And there you go, a beautiful chain reaction. As always, export the FX file and test it in the world to see the full effect in-game. But wait, you might have noticed something is missing, a bloom effect. Let's add that next. Unlike Photon 1, Photon 2 doesn't have a separate bloom toggle. Instead, it uses HDR rendering, where any color value greater than 1 will produce bloom automatically. This approach is more flexible and aligned with modern rendering pipelines. You can also tweak bloom settings in the config file, including its strength and blur radius. Back in the editor, open the Resources panel and add a new folder to store materials used in our tutorial series. Right-click to create a new texture material, then double-click to edit it. You can either use the file browser or type in the texture path. Make sure the path follows the Minecraft resource pack location. Here, we'll use a default texture. Adjust the discard threshold to control alpha discard. Photon2 also supports built-in pixel art, and you can use the bit setting to control the pixelated look. Now, drag the material onto your emitters material, and you'll see it takes on a pixel art style. Double-click the material again. Set an HDR color value for bloom. The mode here allows you to control how the HDR color blends with the particle color. Look at that! Bloom is here. You can also apply this material to the trail. Even if the color patterns aren't perfect, the overall visual effect is not bad. Finally, export the FX and test it in-game. You'll see a bright, glowing chain firework effect. It may not be a well-designed VFX, but it's a great way to understand how Photon works under the hood. In this second demo, we'll create a visual effect similar to the logo animation shown in the teaser video. We'll use particles to dynamically form text, visually impressive and stylish. To do this, we first need a mesh representing the text. If you're not familiar with 3D modeling, you can use Blockbench to create one. However, since LDLib2 improves Neo4j's support for complex OBJ files, Blender is a more modern and flexible choice. Open Blender and start a new project. Delete the default objects. Press the Ctrl and A to add a text object. Press the tab, switch to edit mode, and type the text you want. Let's take Hello World as an example. In the right-hand text settings, you can also change the font. It's best to choose one with a simpler structure and fewer mesh faces. After that, press the tab to switch back to the object mode. Click the Object button on the left top to convert the text into a mesh. You'll see that the mesh has relatively few faces, which is ideal for particle-based effects. Next, export the mesh as an OBJ file. You'll get two files, an OBJ file and an MTL material file. To use the OBJ in Minecraft, you need to load it through a JSON model. Be aware that Neo4j uses a slightly modified OBJ format, especially in how it handles material files. We'll need to do some minor adjustments, but it's straightforward. First, inside the LDLib2 assets folder or your custom resource pack, under your namespace, create a models folder and an obj subfolder inside it. Move the OBJ and MTL files into this folder. Open the MTL file. Since no material was defined during export, it may be empty. But Neo4j doesn't accept empty material files. To fix this, simply add a default none material. Type in new MTL none and save it. Next, open the OBJ file. Find the lines that define smoothing groups. These start with the letter S followed by a number. Below each of those lines, add a reference to the material we just created. Type int useMTL none and save it. This tells Neo4j what material the mesh should use. Now we need to create a JSON file to load the OBJ model. Because of Minecraft's model structure, this file must go into either the block or item folder. So we'll create a new JSON file under the block folder and specify the path to our OBJ model. Just like this. Full parameter documentation is available on the Neo4j website. We don't use textures here. If you need it, you'd better check document in details. Once saved, launch the Photon Editor again. Let's start by creating a new project. Now, let's import the OBJ model we made earlier. In the Resources panel, select Mesh, right-click to create a new mesh asset. Double-click to edit it, click Select a Model, and choose the JSON file we prepared. Keep in mind, if the JSON file was added after the game started, Minecraft may not load it yet. In that case, click Reload Mesh to refresh. If it still doesn't show up, try clicking it again. Once the mesh loads, you'll see its wireframe appear in the scene. Now create a new particle emitter. In the Shape settings, select Mesh and drag the imported mesh into the field. The mesh outline should now be highlighted in the scene. Next, set up a burst, firing 500 particles at time 0. You'll start to see the shape of the text formed by the particles. Let's scale and rotate the mesh a bit to better fit the scene. To make the particles gather and disperse, we'll use noise. Enable the noise module and add position offset noise. Use a curve to control the noise over time. Start with a high offset, fade it to 0, and then increase it again. It gives a very dynamic and eye-catching motion. To make the appearance softer, let's add a fade effect. Under Color over Lifetime, adjust the transparency at the beginning and end. This creates a nice fade in and fade out. Now let's add an HDR glow effect. Create a new material, set its HDR color, and assign it to the emitter. Restart the FX. Yes, that looks amazing. Finally, export the FX file and test it in-game. With bloom and shaders enabled, this effect looks stunning. I'm sure you'll love it. In this final demo, we're going to create a force field effect, something you've probably seen in many modern games. In engines like Unity or Unreal, this kind of effect is usually built with a shader graph, which makes it very easy to design and customize. We also plan to introduce a shader graph system in Photon in the future, so stay tuned for a much better shader authoring experience. Without shader graph, Photon2 also supports this kind of effect, but it requires writing custom shader code. So in this demo, we'll try to replicate a basic force field. A quick note, this part is not beginner-friendly. If you're not familiar with shader programming or the rendering pipeline, it may be challenging. But we hope this demo gives you a simple introduction to custom shader materials in Photon and offers advanced users more creative freedom. One more reminder, this demo includes knowledge beyond Photon itself, such as GLSL shaders, the Minecraft rendering pipeline, how models are loaded, and Minecraft shader JSON format. If anything seems unclear, we recommend looking up related resources on your own first. This video is not a tutorial of Minecraft development. Now let's begin. I've already created a sphere model in Blender and exported it as an OBJ file. Then I converted it into a JSON model, just like we did in the earlier demos. Back in Photon Editor, create a new project and add a particle emitter. Set the shape to dot and make it emit just one static particle at spawn time. In the renderer section, change the render mode to model and select the JSON model we just imported. Click Restart, but you might notice nothing is rendering. That's because Block UV is enabled by default. This setting tells the renderer to sample textures from the Minecraft block atlas. If your model uses standard Minecraft textures, this works. But in our case, we just want to use standard UVs from 0 to 1. So we disable Block UV. Now the model renders, but it looks strange. That's because the default material is semi-transparent. Let's temporarily switch it to the missing material to see the model clearly. Much better. That's what we expect. You might also notice the model seems offset from the center. That's because NeoForge shifts imported OBJ models by 0.5 meters to align them with Minecraft's block-centered coordinate system. To fix this, simply add a pivot offset of 0.5 on all 3 axes in the particle settings. And finally, you can scale up the model using the size or transform settings to make it look like a proper force field. Next, let's prepare the shader for our force field material. Minecraft provides a JSON-based shader program system which allows us to define how a material should be rendered. Specifically, developers can use a JSON file to specify which vertex shader and fragment shader to use, as well as declare any required samplers and uniforms for the program. Minecraft also offers built-in support for certain uniforms, such as game time, screen size, fog parameters, and more. On top of that, LDLib2 and Photon have extended this system. You can now attach a geometry shader and make use of additional built-in uniforms and samplers. You can check the full list of supported additions on the wiki. Moreover, LDLib2 allows you to interactively adjust custom uniform values inside the editor, which is especially helpful for shader development and live previewing. We will have a try later. Please note, this is not a Minecraft shader tutorial, so we won't go into too much detail about the structure or syntax of Minecraft shaders. We assume you're already familiar with how the shader pipeline works in this context. Now let's look at a basic shader material, JSON. Its structure is very similar to Minecraft's built-in particle program. The main difference is that we're using our own vertex and fragment shaders here. In the vertex shader, we start by declaring a GLSL version of 330 or higher. This is important because Photon supports different emitter types that may use different vertex data layouts. For example, with or without GPU instancing, or with custom GPU-side data structures. To make our shader material compatible with all these variations, Photon provides a shared particle shader library, which can be imported using the Mojage import directive. This library defines macros that automatically handle the vertex input data and wraps it into a unified structure called particle data. This structure gives you convenient access to processed attributes like position, color, UVs, lighting, and normals, similar to what you get in Minecraft's native shaders. In the vertex shader itself, we follow the standard approach, apply view and projection transformations, and then pass the necessary data to the fragment shader. Inside the fragment shader, the logic becomes even more familiar. It closely resembles Minecraft's default shader code. The only difference is that we don't sample from a texture, since this particular effect doesn't need one. After applying fog calculations, we simply output the final color. Now, let's create a custom shader material. Double-click the material to edit it and select the JSON shader file we just wrote. Keep in mind that Minecraft requires shader files and their JSON definition to be placed under the shader's core directory in your resource pack. Now apply the material to the shield object in our scene and preview the result. As expected, it renders correctly, because in our fragment shader, we're simply outputting the particle's base color. Next, let's improve the shader by adding a Fresnel effect. This is a very common technique in VFX, used to create glowing edges by adjusting brightness based on the angle between the view direction and the surface normal. To achieve this, we first need to modify the vertex shader. We'll pass two pieces of data to the fragment shader, the view space normal and the view direction, which is the vector from the vertex to the camera in view space. The view space normal can be calculated from the vertex normal using matrix transformations. Then, in the fragment shader, we add inputs for view direction and view normal. Here's the formula we use to compute the Fresnel intensity. We take the dot product of the two vectors and raise it to a power using POW. This gives us a smooth edge highlight based on viewing angle. Once the shader is updated, click Reload Shader in the Material Editor. You'll now see the Fresnel effect working. Try adjusting the power value, you'll notice different levels of brightness on the edges. However, testing different power values in the code is inconvenient. To fix this, let's expose power as a uniform. Add a uniform declaration in the fragment shader, and don't forget to define it in the JSON as well. After reloading the shader again, you'll see that a text field for power appears in the editor automatically. All custom uniforms are detected by the editor, which makes it much easier to tweak shader effects in real time. Next, let's give the shield some HDR color. Just like before, we define a new HDR color uniform and modify the fragment shader to use that color in its final output. After reloading the shader, you'll see a color picker appear for the HDR color. Photon automatically recognizes any uniform fields that include HDR in the name and provides a built-in color editor for them. Now, You can freely adjust your material parameters until you're satisfied with the result. Pretty cool, right? Finally, let's add a highlight effect at the intersection between the force field and other meshes. This is another technique commonly used in modern games. To achieve this, all we need is access to the depth texture, then calculate the difference between the background depth and the shield's depth to control the intensity of the effect. We won't go through the code line by line here, as the concept is quite straightforward. Photon extends the shader program system by providing additional built-in uniforms, including the inverse of the projection matrix, as well as access to the scene color and depth textures. You can declare these resources in the material JSON file. Because we're calculating fragment depth in the vertex shader, we'll pass the view space position directly to the fragment shader, instead of just the view direction. Then in the fragment shader, we compute the shield's depth in view space, compare it with the background depth from the depth texture, and highlight regions where they are close, creating a subtle, glowing edge at the points of intersection. The concept is simple, and if you were able to understand the Fresnel effect earlier, I'm confident you'll be able to implement this part as well. And that brings us to the end of this video. If you've made it this far, you're definitely someone who enjoys VFX. We look forward to seeing the amazing effects you'll create using Photon. Thanks for watching, and see you next time.